Hi everyone, welcome back to AP Physics. So we kind of wrapped up the first big topic in the first part of physics, which is mechanics, kinematics, right? Talked about motion, how things move, right? We talked about displacement, we talked about velocity, we talked about acceleration, right? Courses of motion, how things move. We really didn't talk about, in a sense, what got them started, right? Why things move. Why do things move, or why do things move the way they do, right? This is really the next kind of foundation of mechanics in physics, which deals with Newton's law of forces, right? So let's jump in right away. So what are Newton's laws of forces? There are three of them, right? First is kind of a law of inertia. You'll be hearing that term a lot. Law of inertia simply states, I mean, different textbook has different wording. The way I look at it is objects in motion will stay in motion unless an external force is applied. If you've taken any physics class, you probably memorize this line and go, oh, what does this mean? Objects in motion will stay in course of motion. The way I like to interpret this is will stay in course of motion means you're going to keep your velocity constant, right? A course of motion, any velocity, right, means you'll be able to, if you can maintain that course, maintain means there is no change, that means your velocity will keep constant, right? That's how you maintain a course of motion. Whether or not that motion is velocity equal to 0 or velocity equal to 20, it doesn't matter. If you have a velocity that's constant, right, you're maintaining your course of motion. So an object in a motion, in whatever motion it is, will stay in a course of motion unless an external force is applied. So when you apply an external force to an object, it implies that we'll change the motion, change the course of motion, or change the velocity. So what that really implies is that if you apply a force to an object, the velocity will change. In other words, if you apply a force to an object, you will have acceleration, right? Because change of velocity is equivalent to acceleration. So really, the second law, or law of motion, which is the one that everyone memorizes, says what? Force, I like to say external force, keep that in mind, okay, is equal to mass times acceleration. Okay? Force is mass times acceleration. I will even change that to say net force is equal to mass times acceleration. Whenever you apply an external force, a net external force, you're going to cause an object to accelerate. And the proportion that acceleration is determined by the mass of the object. This concept of net force is very, very important. Okay? It has to be a net force that's causing your acceleration. It's not a single force. It's all the force combined. The sum, the vector sum of all the forces, that net force is going to lead to this acceleration. Okay? What does that mean? Let's say you have an object right here in the middle, right? If I apply force in this direction only, that is going to be my net force. Okay? If I apply force in the opposite direction with the same magnitude, what is your net force? Your net force in this case is going to be what? 0, which means you will not have any acceleration. Okay? The key here is net force. Right? So how do we measure force? Well, let's take a look at a unit, right? Mass has a unit of kilograms, right? Acceleration has a unit of meters per second square. So 1 kilogram meter per second square is actually equal to 1 Newton. You know that already, right? Named after the most famous physicist, right? Force is equal to ma, and that is the force net force. That's important. Okay, not just any other force, right? So after that's been emphasized, the third law of action and reaction. Law of action and reaction, just the way it sounds, right, means anytime you apply a force, you can look at it from the other perspective. There's a reaction force applied to you. For instance, if I'm leaning against the chalkboard, right, from my perspective, I'm applying force to the chalkboard, right? The chalkboard, on the other hand, is applying force back at me. So the two forces cancel each other out, and my net force in this case is 0, and that's why I'm not moving. I'm not accelerating in a certain direction. That's the law of action-reaction. Every force of action is reacted with a reaction force. Okay? Keep that in mind. So it's really, really important to kind of understand this concept of net force. So why don't we just kind of look into that a little bit? So, if I have an object that's being pulled in this direction, right, and have another object, another force that's applying this direction, what's my net force? Which direction is my object going? Well, how do you find a net force? Net force is what? Net force, in other words, is the vector sum of all force vectors. Okay? It's a vector sum of all force vectors. So I'm going to move, what's the sum of these two vectors? Again, remember how you manipulate vectors? You move the F2 over there, right? And this is your force net. So if you have someone pushing you this way, someone pushing you this way, right? You're actually going to end up moving in this direction with an acceleration. So always, always make sure that you find out your force net first. Okay? So that's kind of the fundamental concept of what causes a motion, what causes acceleration, because acceleration is the fundamental factor that drives motion. It drives a change in velocity, it drives a change in course motion. What causes that is an external force, right? All the external forces add up together, you produce this net force that induces your motion. Okay? So, how do we solve any of these kind of force problems, right? I'm going to bring up something that you heard a lot, but probably didn't pay attention to. The method to solve all Newton's law problems is using the free body diagram method. And I have boiled that down to an art, 3 simple rules that you need to follow, and you'll be fine. Okay? So, let's take a look at the free body diagram. All right? What do we have is, let's say I have this box in the middle. All right? I'm pushing with the F1, right? And then I'm also pushing with F2 of the same magnitude, but 45 degrees. Okay? I want to know what is the acceleration and what direction would it accelerate. Right? So, free body diagram. 3 simple steps. Number 1, I want you to label all forces that's acting on this box. Okay? Done. Force 1 this way, force 2 this way. Right? Very simple. Number 2, all forces. Define x, y coordinate plane. Okay? I want you to define an x, y coordinate plane. Meaning what? You have to have, you know, a coordinate system, whether it's positive or negative, right? Yeah, usually I just go x positive, y positive, right? X positive, y positive. And then number 3, which is kind of the most important and the most crucial, is what? Decompose all forces into x, y plane. Okay? Everything needs to be in the x and y plane. Right? Think about this. Well, F1 is fine. If I define this as my xy plane, F1 is fine. F2 is not. Right? Why is F2 not? Because it's sticking out, right? It looks weird. So what do I do with F2? F2, this will be my F2y and F2 of x. Right? F2 of y will be F2 times sine of 45, right? F2 of x will be F2 times cosine of 45. So I get F2y and F2x. Okay? You decompose all the forces into xy plane, and then you can write 2 expressions. F net of x is equal to mass times ax, and F net of y is mass times ay. Okay? F net of x is mass times ax. F net of y is mass times ay. What does that mean here? Well, here, F net of x, meaning I'm adding up all the forces in the x direction. Right? What I have here, I have F1. I also have what? F2x. Right? F1 F2x. This case is mass of the box times ax. Right? F net of y will simply be what? F2 of y, because that's the only force in the y direction, right? Again, I define positive and negative, so it's easier, right? And which will be just what? Mass times ay. So you get your a component of a in the x direction, you get your component of y, a in the y direction, right? And you find the final acceleration. Okay, that's how you tackle these problems. That's how you tackle free body diagrams. Don't worry about it. We're going to do a lot of these problems. I'm going to show you a lot of examples, and you'll see how that's actually being done. So what I want to do right now is take a look, keep this in mind, take a look at some of the important forces. Okay, we're going to take some important forces that you have to take a look at and to deal with. The first force that you really have to deal with that's always around is what? This force called weight, or W. What is weight? If you think about it, if I put an object on a flat surface, right? This object is constantly getting what? Getting pulled down by gravity. And I know if there's an acceleration, there has to be a force, right? In this case, the force is what? The gravitational force acting on a box because it's mass. So we call that weight. And if you think about it, force is m times a. In this case, I know what a is. A is simply g. So weight is simply just m times g. So almost every object you deal with, right? When I say almost, I mean unless it's out of space, there's no gravity, that's fine. But every other object you deal with has to be dealing with this concept of g. Okay? Or, in other words, an object experienced with g, which is the weight. Every object has weight. Weight, always remember, always points straight down. That becomes important when you deal with other problems, because if you have an inclined surface, which direction is your weight? Your weight is not this. Your weight is what? Your weight is that. So always pointing straight down. Okay? Just a convention. All right. And if you think about it, there's a weight, but if that's the only force acting on this guy would be falling through. It's not, right? Because it's supported by a surface. Right? So this guy, the surface, has a reaction force against the weight. Right? Which means this box feels the reaction force in the opposite direction to balance it out. Right? In this case, this is what we call the normal force. Okay? Normal force. Normal force is always perpendicular to the surface. Keep that in mind. It's very important. So in this case, your normal force and your weight are in the opposite direction, same magnitude. They cancel each other out. That's why what? Your box doesn't move. Right? Your box doesn't move. However, if it's on an inclined plane, your weight is coming down. Your normal force is the same magnitude, but going in that direction. Right, a different magnitude going in that direction, you have what? These forces no longer cancel out. If you think about it, you have an extra component of weight that's dragging this guy down. Okay, that's dragging this guy down. But just keep in mind, if it's flat surface, normal force should be equal to whatever the force that's acting down, right? But in this case, it's always perpendicular to the surface. Okay? Last but not least, the third component force that you always have to consider is this concept of friction or frictional force. Often use lower letter F to describe it. Frictional force is a microscopic force that's always there. You might in high school, at least in high school physics, you might have told, oh yeah, you can ignore it, assume it's frictionless. In AP, it's almost always have friction. Where does this come from? Right? Where does this friction come from? Think about it. If I zoom in here, right? Let's say I'm trying to move this guy, apply force, trying to move this guy in this direction, whatever. If I zoom in here, this surface is not smooth, right? Because on a molecular level, if I zoom in, the box looks like this, right? It's not flat surface. You learn from chemistry, right? And then the bottom, the surface it's trying to move against, looks like that. So imagine you try to move the purple across from the orange, there's going to be bumps. We can't see them. They're microscopic forces. We can't see them, right? They're too small. They're at a molecular level. We can't see them, but in reality, they do exist. So they have to what? They have to overcome the bump, right? So basically, frictional force is always in the opposite direction of applied force, right? It's basically the party pooper. You want to move that way, you want to push a box that way, friction force is going to be opposite direction. You want to move it up, it's going to go down. Friction force is always against the motion. Keep that in mind, opposite direction, right? Now, there are different levels of friction force. It could be strong, right? There are surfaces that are really smooth because there's a surface that's more like this, and the other surface that's more like that, right? That's a little bit more smooth than this case, which is what really rigid, right? But friction always exists. So how do we take into account of friction? If you think about it, friction force really has to do with what? Two things. One is how rough your surface is, right? If you have a rigid surface that looks like this and the bottom looks like that, it's just really difficult, right? As opposed to a little bit smooth, right? It's less friction. So it depends on the materials that you have, or in this case, mu, or friction coefficient of friction. right? Coefficient of friction. And this is a material constant that depends on what surface you have. It's different for every different case scenario. Okay? So usually in a problem, they give it to you. That's fine. What else does it depend on? It also depends on what? The interaction between the object and the surface. If the object, if for the same rigid surface, right? If it's pressed against it, the friction will be a lot greater, right? If it's a little bit lifted, then, not so much. So it's not necessarily the weight, but it's a pure, like the contact force, right? In other words, your normal force. So friction is always mu, your coefficient of friction, times n, your normal force. So see, everything links together, right? Your normal force is a reaction to your weight, and friction is dependent on your normal force and opposing whatever the applied force you want to have. Okay? So, let's go back to our example of the, so keep this in mind. Let's go back to our example of having our box. I have a box sitting right here with a certain mass of m, whatever m is, and I'm applying a force in this direction to push it. How do I solve this problem? How do I get the acceleration of this problem? Guess what? Use the free body diagram, right? First, you say, all right, label all the forces. What are the forces acting on this box? One, there's what? There's always weight, which is m times g. Right? There's your normal force, which is perpendicular, right, which is n. And then there's what? Your friction force, which always acts against the pushing force, right? In this case, it'll be friction. Right? So I label all the forces, done. Define your xy coordinate plane. So, right, this will be positive, this will be positive. It's fine. Right? And then you find your force net of x, force net of y. That's easy. Force net of x will simply be what? Force minus friction, right? Force is positive, friction is negative. It's going to be equal to m times ax. Force net of y will be what? Positive is normal force minus the weight, which will be mass times ay. Let me tell you about ay. What is ay in most cases? Ay in most cases will be what? Will be 0. Because you never, if you apply force in this direction, you can never imagine the box move up and down. Right? This normal force and this weight usually what? Cancels each other out. Right? So that's going to be equal to 0, which means what? Your weight is your normal force or equal to mg. Right? And then what you're looking for, ax, is really just your acceleration. So if I'm giving this force, you know friction is what? Mu times normal force. Or in this case, I know normal force is what? Mg. So mu times m times g. And then you can find out what your acceleration is. Okay? So that's how the workflow goes with Newton's law. Right? So a couple of very important things. I would like today's lecture, like 3 sectors. 1, know the 3 basic laws, right? First law, second law, third law, right? Most important thing is that when they talk about force is equal to ma, it's net force is equal to ma, right? Number 2, once you get that, look at the free body diagram. How do you solve every single problem with free body diagram? Label all the forces, define your xy plane, decompose all the forces into xy plane, which cases already are, and then do your force net of x, force net of y, tabulate them. In a lot of cases, force net of y, the ay is going to be equal to 0. Right? And last, the 3 fundamental forces you're always going to be dealing with. 1, your weight. Number 2, your normal force. Number 3, your friction. Okay? We're going to see a lot of interactions in the next lecture. The basic concepts out. I'm going to deal with how to solve these problems, how to look at these problems, and use the same approach. So if you understand approach, every single problem needs to be solved with the same approach. And these problems will become very straightforward, very easy. No confusion, okay?